Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element Protactinium. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Protactinium is the 91st element in the periodic table. Its atomic number is 91 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Dmitri Mendeleev, often considered one of the fathers of the modern periodic table, was trying to make sense of how the elements related to each other. The table was originally published in 1869. An important aspect was that Mendeleev knew that he didn't know about all the elements, and he left some empty spaces where he believed elements were yet to be discovered. In particular, he left a space between thorium and uranium for an unknown as yet element. He called this element tantalum because it fell below the element tantalum in his chart. This was a mistake. He believed this undiscovered element would have some of the characteristics of tantalum. The actinide series of elements were as yet unknown. More on this later. William Crookes was able to isolate protactinium from uranium in 1900. It was highly radioactive, far more radioactive than uranium. Unfortunately, he could not determine that he had found a new element. He called it uranium X. Protactinium was first identified in 1913 by Kazimierz Fajans and Oswald Gehring. They were studying the decay chain of uranium-238, and protactinium was a daughter product of uranium decay. More on that later. They named the element brevium, from the Latin word for short, because of the element's short half-life. Fajans and Gehring were seeing the isotope protactinium-234M, an excited nuclear state of protactinium-234 with a half-life of 1.16 minutes. About 4 years later, two groups discovered another isotope. Lisa Meitner and Otto Hahn in Germany, and Frederick Soddy and John Cranston in Britain independently found protactinium-231, an isotope with a much longer half-life. Frederick Soddy described how one element turned into another by radioactive decay, called transmutation, and also gave us the concept of isotopes. He was awarded the 1921 Nobel Prize in Chemistry. Lisa Meitner, Otto Hahn, and Fritz Strassmann at the Kaiser Wilhelm Institute for Chemistry discovered atomic fission. However, only Hahn was awarded the Nobel Prize for this in 1944. Many people thought this was wrong. Meitner was nominated 49 times for Nobel Prizes, but was never awarded one. Her ultimate reward was to come in 1997 with the posthumous naming of element 109, meitnerium. Aristide von Gross, seen here playing with a bubble, all physicists love bubbles, was the first to isolate metallic protactinium in 1934. He called the element protoactinium. Here's why. The element was named from the decay chain that produces it. Uranium decays to thorium, then to protactinium. The protactinium then decays to actinium, from the Greek protos, meaning first or before. Aristide von Gross named it protoactinium since it came before actinium in the chain. Lisa Meitner and later the IUPAC, the International Union of Pure and Applied Chemistry, shortened the name to protactinium. In nature, Wherever you find uranium, you usually find a bit of protactinium. It's in the decay chain. Radioactive decay of the uranium causes both these minerals to contain protactinium as well. More details on this later. Uranite, also known as pitchblende, is a radioactive uranium-rich mineral and ore with a chemical composition that is largely uranium dioxide, but because of oxidation also typically contains variable proportions of U3O8, triuranium octoxide. Carnotite is a potassium-uranium vanadate. You can see the uranium in both their chemical formulae. Though these uranium-rich minerals contain protactinium, there's too little protactinium to mine them as a viable source. Most protactinium comes from the reprocessing of spent nuclear fuel. The stand-in for Theodore Gray's photo of protactinium is another uranium-bearing mineral called tobernite, a hydrated copper uranyl phosphate. Again, protactinium is a decay product of the uranium, which you can see in its formula. There's probably a few atoms of protactinium in this sample at any given time. The green color is probably from the presence of the copper in the mineral. It was named for the Swedish mineralogist and chemist Torbjörn Olof Bergman. The UK Atomic Energy Authority produced 127 grams of protactinium-231 in 1961 from 60 tons of waste material. This would be a cube 2 centimeters, a little over 3/4 of an inch, on a side. This was a huge amount. It cost about $500,000 to produce this, so doing the arithmetic, I guess protactinium went for about $4,000 per gram in 1961 dollars. The Oak Ridge lab in the United States later produced and supplied it for the low price of $280 per gram. What a bargain! Protactinium is a member of the actinide series of elements down at the bottom of the table. It's the third element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides are radioactive. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 91 protons for protactinium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 29 known isotopes of protactinium, and we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of protactinium are radioactive. As we'll see in the next slide, all the half-lives of protactinium are fairly short, but long enough we find a trace of them in nature as decay products of other radioactive elements. More on that in a couple slides too. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of protactinium occupy the same place in the periodic table. Of the isotopes of protactinium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest protactinium half-life is protactinium-231, with a half-life of 32,760 years. It makes up virtually all the protactinium found in nature. A trace of protactinium-233 and 234 are also found as byproducts of decay from other elements. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1024 atoms of any isotope from the previous slide. I chose 1024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait 1/2 life, half of your isotope will decay, and we'll have 512 atoms left. If we wait one more half-life, half of that half decays, leaving us with 1/4 of the original 1024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice there's one remaining atom after 10 half-lives. If we waited one more half-life, our remaining atom would have a 50-50 chance of decaying in that time. I've mentioned that all protactinium is from radioactive decay of other elements. Let's look at that. I want to show you some of the decay series that lead to protactinium, and I want to do it on a chart you'll see in many physics texts, and which I'll attempt to show you in the next slide. We're only using a very small portion of this much larger chart. On this chart, the horizontal axis shows how many protons plus neutrons are in the nucleus. This is related to the atomic weight of the isotope. The vertical axis is the number of protons in the nucleus, its atomic number. Since the atomic number also tells us what element we're dealing with, each row is one unique element. Generally speaking, when an isotope decays, it can do this by emitting an alpha particle or a beta particle, and I'm oversimplifying this. An alpha particle is made up of 2 protons and 2 neutrons, 4 particles in total. So if we start with something like radium-226, it has 88 protons. All radium isotopes have 88 protons. Radium-226 decays by alpha emission, meaning it loses 2 protons and 2 neutrons, 4 particles in total. This means we need to move 2 rows down for the 2 protons and 4 rows to the left for the 4 total particles. You can see we arrive at radon-222. Okay, this is the move for alpha decays. What about betas? Here, one of the neutrons in the nucleus becomes a proton and an electron, and the electron is spit out of the nucleus as a beta particle. This means the nucleus gains a proton, but does not change its atomic weight significantly since electrons are so light. This time, we'll start with thorium-234. Gaining a proton, but not changing its atomic weight, moves us up 1 row, and we now have a new element, protactinium, but with the same weight, 234. This is what beta decay looks like on our chart. Let's take a peek at the whole chart. Here's the portion of the chart of the nuclides that contains a row for protactinium, but let's back away to see the whole chart. Here you see all the stable and radioactive isotopes we know or speculate about, from hydrogen down in the lower left through the as yet undiscovered element 119, temporarily named Uranium. But back to our decay series. We'll start with the most common uranium isotope, uranium-238. Uranium-238 has a half-life of 4.5 billion years. I'll list the isotopes, decay mode, and half-lives at the top for your reference. Uranium-238 decays by alpha to thorium-234. Thorium-234 decays by beta. Remember, we move up 1 square for betas into this program's element, Protactinium-234. That decays by beta into Uranium-234. Note, this uranium is a different isotope than the one we started out with. Uranium-234 decays by alpha to Thorium-230, again a different isotope than the thorium before. Thorium-230 decays by alpha into Radium-226. This is the most common and longest-lived radium isotope with a half-life of 1,600 years. Radium-226 decays by alpha into Radon-222. Radon-222 decays by alpha into Polonium-218. This short-lived Polonium-218 decays by alpha into Lead-214. Lead-214 is a radioactive form of lead, which decays by beta to Bismuth-214, which decays by beta into Polonium-214, which almost immediately decays by alpha into Lead-210, another radioactive form of lead, which decays by beta to Bismuth-210, which decays by beta to Polonium-210, our third isotope of polonium in this decay chain. This polonium finally decays by alpha to Lead-206, which is stable and not radioactive. Quite a roller coaster ride from uranium to lead. Remember, our original Uranium-238 had a half-life of 4.5 billion years. Since Earth is about 4.5 billion years old, about half of the Uranium-238 on Earth has decayed to lead. Natural uranium is mostly Uranium-238. A small portion, only 0.7%, 1 out of every 142 uranium atoms, is the isotope Uranium-235, our starting point for this decay chain. This decay series is often called the actinium series, so as not to confuse it with the uranium series we just saw, which started with Uranium-238. I won't bother you with the details of this decay chain, but through a series of transmutations, Uranium-235 eventually decays to Lead-207, which is non-radioactive and stable. Note that Protactinium is part of this series too. Lastly, we'll talk about the neptunium series. Here, we obviously start with neptunium, specifically Neptunium-237, a natural byproduct of uranium decay and, more commonly, a product of fission in nuclear reactors. Again, I won't bother you with the details, but neptunium decays through Protactinium-233 to eventually end up as Thallium-205, which is stable and not radioactive. This is the only decay chain we've seen so far that does not end in a stable lead isotope. So, with all these 3 decay series, we've accounted for virtually all the protactinium that occurs in nature. The longest-lived, Protactinium-231, and the trace Protactinium-233 and 234. Since we're on our 8th radioactive element, 9th if you include bismuth, I'd like to repeat how radioactivity is measured. There are 3 interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity, the rate particles are emitted. This is probably the simplest thing to measure. You can use a simple Geiger counter and just count the number of detections per second, but you need to take into account the size or area of the detector and its distance from the source and multiply the measured counts per second as if your detector could completely surround the source to catch all the disintegrations in every direction. The international unit for this is the becquerel, named after the discoverer of radioactivity, Henri Becquerel. 1 becquerel equals 1 disintegration per second. So most sources are in the kilo, mega, or even gigabecquerel range. In the US, we also use an older unit, the Curie, obviously named after our dynamic duo, Marie and Pierre Curie. 1 Curie is the amount of radiation given off by 1 gram of radium, discovered by them, get it? 1 Curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Radiation carries energy, and that energy is deposited in your body, or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is the amount of energy used to lift an apple from the floor to a table, approximately. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A Gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milli or micrograys or something like that. In the US, we've used the unit of the rad, or the Roentgen absorbed dose, which is 1/100th as large as the Gray, but still a large amount of radiation. Roentgen, by the way, discovered X-rays in 1895. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation, alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to the specific kind of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the US, we also use the rem, which stands for Roentgen equivalent man. The sievert is just 100 rem, and the rem is 1/100th of a sievert. These are human health-based units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer, genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts, or 5 rem, per year in the workplace. You normally absorb about 67 millirem every year from the environment around you. That's 1/75th of the allowed annual dose. A dental X-ray exposes you to about half of a millirem. A standard chest X-ray, front and side, exposes you to up to 10 millirem. And a chest CT scan gives you up to an 800 millirem dose. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits always outweigh the risk. I normally talk about the abundances of the elements on this slide, but because of the short-lived radioactive nature of protactinium, there's not much to say here. There's really none to speak of in the universe, having all decayed away by now. And none in the sun for the same reason. Likewise, none in meteorites. And not really enough in the Earth to talk about except the tiny amount resulting from the decay of other elements, right down at the bottom of our chart in 85th place, making up only 9.9 parts per quadrillion of the Earth's crust. It's virtually absent in the oceans, also at the bottom of the chart, making up 200 parts per octillion. You don't get to use that fraction very often. And of course, thankfully, none in us. That was a lot of red X's. As I just mentioned, there's a bit in the crust from radioactive decay of other elements. It's estimated in the crust of the Earth there's around 27 metric tons of protactinium. If you could magically collect all that protactinium from the entire Earth, you'd have a cube about 121 centimeters, or about 4 feet, on a side. That's a human-sized cube, though much, much heavier and extremely radioactive. Remember, you have about the density of water. More on that in a bit. Protactinium is not mined, refined, or manufactured for any commercial reason. Virtually all protactinium is produced for research purposes, and this is extracted from spent reactor fuel pellets. 2 slides ago, I mentioned protactinium's high density. In fact, protactinium has a density of 15.37 grams per cubic centimeter. It's a pretty dense element. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds. As you can see, it's between the density of lead and tungsten. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, protactinium's density is 15.37 grams per cubic centimeter, near the top of the chart, the 11th densest element. Because of its highly radioactive nature and rarity, I won't be adding a block of this element to my collection. Protactinium has a melting temperature of 1,572 degrees Celsius. That's 2,861 degrees Fahrenheit. That's the 18th highest melting point, close to the top of the chart. Protactinium boils at a blistering 4,000 degrees Celsius, or 7,232 degrees Fahrenheit, giving it the 15th highest boiling point of all the elements. That's about 2,428 degrees Celsius above its melting point, giving it the 9th largest liquid temperature range of all the elements. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range, all the way down to neon, which is liquid only in a 2.51 degrees Celsius range. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. Protactinium has the 9th widest liquid range at 2,428 degrees Celsius. If we compare the size of the protactinium atom to that of hydrogen, we'd see something like this, though I'm just estimating the atomic diameter since it hasn't been measured accurately yet. The protactinium atom is about 4.7 times the size of hydrogen. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are outstandingly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. My estimated size of the protactinium atom places it in the upper region of the chart, maybe around the 6th largest atom, about the same size as some of the rare earth lanthanides above it in the chart. Not too surprising, since the actinides share many properties of the lanthanides above them in the periodic table. I'm highlighting the lanthanides in blue. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of protactinium, a nice selection of reds and oranges, completely lacking any greens or blues, but including a few violet colors. Spectra of the elements uniquely identifies them to scientists, as each gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Aside from research applications, there's not much to say here. This is a small sample that proclaims to be actual protactinium inside a glass vial. I have my doubts. In proposed thorium reactors, protactinium is a precursor to the production of fissile uranium. We start with thorium-232, the longest-lived isotope of thorium. When hit with a neutron, it becomes a different isotope, thorium-233, with a much shorter half-life, only 21.6 minutes. That decays by beta to protactinium-233, with a half-life of only 27 days. The protactinium-233 then decays by beta to uranium-233, with a fairly long half-life, almost 160,000 years. So far, there have been no fissions or neutrons that can cause further fissions in a chain reaction. Uranium-233, however, like uranium-235, is susceptible to fission if it absorbs a neutron and can take place in chain reactions. Uranium-233 is fissile. Thorium and protactinium, while not fissile, are subject to transmuting into another element that is fissile. Thorium and protactinium are labeled as fertile. There is a fly in the ointment complicating this process, however. The protactinium tends to absorb some of those extra neutrons, poisoning the uranium chain reaction. So this protactinium must be removed from the active zone of the reactor. Using both thorium-230 and protactinium-231 helps oceanographers more accurately date sediments at the bottom of the oceans. Protactinium-231 has a 32,500-year half-life, and thorium a 75,400-year half-life. Measuring the amounts of both isotopes and looking at the ratio of the two are a better measure of age than either of them separately. It's all about teamwork. This method works to date sediments up to 175,000 years old. These ages can be used to determine ancient sea levels. The only other applications seem to be helping characterize the elements of the actinide series. These are research only and are not practical applications, but who knows where the research will lead? Protactinium serves no known biological purpose and is so short-lived you shouldn't find any inside you. Well, hopefully. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about protactinium. Both of your neighbors prefer nuclear power. You clog reactors. In the next program in this series, I'll examine uranium, one of the last few elements with significant applications, far more than protactinium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element protactinium. For more Tales from the Periodic Table, see this playlist on my YouTube channel. And of course, I'm required to say this by law, smash that subscribe button.